Hello everyone, and welcome back for Chapter 2, Unit 1B for Geometry. This chapter is all about reasoning and proof. In this chapter we are going to be learning about two different types of reasoning, inductive and deductive reasoning. We discussed a bit the difference between these two. So for your warm-up question, I'd like you to please define the differences between these in 2 to 3 sentences. Pause the video and write your answer below. Alright, double check your answer for inductive and deductive reasoning. Make sure your answer sounds something along these lines. Inductive reasoning means making an educated guess based on patterns, hints, and clues, whereas deductive reasoning is drawing definite conclusions from other facts. The first thing we're going to be working on from Chapter 2, Section 1 this time are making conjectures based on inductive reasoning. Conjectures are a concluding statement reached using inductive reasoning, so it's a conclusion. We are going to look at some patterns and draw conclusions to begin. So first, I want you to write down how do you see this pattern growing, and explain yourself in 1 to 2 sentences. Now, I'd like you to create a table of values and a graph to visually represent the total number of boxes in each figure. For example, on the table, in case 1, there's 1 box. Case 2, there are 3 boxes. Case 3, there are 6 boxes, and so on. Fill in the rest of this table on your own. Now, how can we fill in the cases that are not shown? Well, let's work together. If we look at the pattern here, we can see, are we adding a certain number? Are we multiplying by a certain number? Let's take a look. First, from case 1 to case 2, we are adding 2. Next, from case 2 to 3, we're adding 3. Next, we add 4. Hopefully you can see the pattern. Between each case, we add 1 more extra each time. So this time, if we want to add 1 extra to get to case 5, we would be adding 5. So 10 plus 5 would make 15. See if you can fill in the rest of the pattern. Once you're finished, try to graph your points on the graph shown to the right. Here's what it should look like visually. Now, I can see this is not a straight line, but in number 3, I'd like you to say, what is the general shape of this graph? Now, this is a challenge question. If you can, see if you could figure out how many boxes would there be in the 100th case. What about the nth case? If you're in honors, go ahead and see if you can try to answer these. If you'd like a challenge, see what you can answer. Alright, now I want you to try one a little more on your own. I have another pattern here. First, how do you see the pattern growing? Go ahead and complete this one. Alright, continue on. Go ahead and make the table of values and the graph. Once you're finished, you can try to answer the questions below that as well. Here is the correct answer for your table, your graph, and the general shape of the graph. The general shape of this graph is linear. It's a straight line. Now, if we want to figure out how many would be in the 100th case, the correct answer is 501. Notice we're adding 5 each time. It says, what about in the nth case? So let's see if we can write an equation here. We can use n for the number of cases, y for the total number of boxes. You should know how to write an equation of a straight line. See if you can answer that question now, if you have not already. Here's the correct answer. 5n plus 1 equals y. If we test that equation out to find our answer for number 4 or any of our cases, it always holds true. Let's also today talk about counterexamples. A counterexample is used to show that a conjecture is not true. It could be a number, a drawing, or a statement. Let's do example 4 together. It says, find a counterexample to show that the following conjecture is false. Now it's already telling us that the conjecture is false. We have to show an example, come up with something that shows why it's false. Okay, so it says if n is a real number, then n squared is greater than n. I believe this was one that we've seen. So we're trying to come up with a number such that n squared is not greater than n. So we have to keep this part. N has to be a real number, but we want to show that n squared is not greater than n. Is there any real number you could think of where n squared, that number squared, is not greater than the number itself? One number you might use is positive 1. Positive 1 is a counterexample. The reason why positive 1 is a counterexample is because it is a real number, but n squared is not greater than n. If we think about it, 1 squared, is it greater than 1? No. 1 is equal to 1, not greater than 1. So we know that sometimes this is true. For example, 2 squared is greater than 2. But when you're looking for a counterexample, you are looking for a number or a photo, a figure, to show when is this false. Why is it false? Let's do another one together. It says if JK equals KL, then K is the midpoint of segment JL. Now just so you know, you can only have 1 point K. You can't have 2 point Ks. You have to have only 1 point K. Now this one's going to be easier to do with a figure or a drawing. So I know sometimes this is true. If JK equals KL, then that means K would be the midpoint of segment JL. But what if we took this as a counterexample? What if JK and KL, what if points J and L were not collinear? Now, is K the midpoint of segment JL? No. Segment JL does not even include point K. We know, again, sometimes this can be true. However, we are trying to come up with an example of when it is not true. So here's my counterexample to show that JK is equal to KL. However, K is not the midpoint of segment JL. I'd like you to try the practice problems below on your own. Pause the video now. Here are some sample answers. And I'd also like you to answer this reflection question. Please come up with your own sequence. That means a pattern of numbers. Write a conjecture about your sequence. That's all I have for you today. Tomorrow, the next time, we will be talking about truth values of negations, conjunctions, and disjunctions. See you then.